In the last segment, we learned that material particles, like electrons, protons, neutrons, they really have a wave-like nature. They act as much like waves as they do like particles. And so, let's run with that idea and see what kind of conclusions we can reach. Here we see a picture of some particle in a box, and this is a classical particle. And so we're going to distinguish between classical physics and modern physics. In classical physics, a particle is a particle, and that is the end of it. Light is a wave, and particles are particles. That's classical physics. So if we put this classical particle in this box, well, what will it do? It'll bounce back and forth. We could measure its position, just fine. It's right there, right? Ooh, I know where it is. And we can measure its velocity. Now we know how fast it's going. No big deal. That's the situation. But what if we try and put a wave in a box? Well, if we try and put a wave in a box, we've actually seen this. We get standing wave. So if I create a sound wave, I don't know, like this. Well, that's not that interesting, right? What happens if I put that sound wave in a box? Here's a pipe. Let's put that sound wave in there. We get a beautiful note. Why? Well, because we get a note that's produced by a sound wave that fits nicely inside of this tube, right? So this is a standing sound wave in this tube. That's why we get the note we heard and not some random other note. If I play it again, we'll get the exact same note. Okay, so that's a wave, a sound wave in a tube. Well, it's hard to visualize. We can do the same thing with a wave on a spring. Here I have a plastic spring, and of course I can create a standing wave on this spring. And this is really some physics 1. We talked about this last semester, right? And so I can produce the n equals 1 standing wave, and I call this the 1 lumper. And notice the frequency, 1,000. It's maybe like a little bit more than 1 hertz, maybe slightly over 1 hertz. 1,000, 2, maybe about 1 hertz. Okay, so that's the frequency. And if I double the frequency, I can produce a different standing wave. Maybe. There it is. If I double the frequency, I can produce a different standing wave. This is the 2 lumper. Here's the 2 lumper. Notice we don't get this beautiful pattern unless we get an integer number of half wavelengths that fit between my hand and that nail over there. This is the 2 lumper. If I wiggle a little bit faster, there is the 3 lumper. If I wiggle a little faster, oh my gosh, there's the 4 lumper, right? So at any rate, I get an integer number of half wavelengths in order to form these nice standing wave patterns. That's what happens when you put a wave in a box. Well, we know that this particle that I've drawn here, well, you know what? If it's a small enough particle, it's going to act like a wave and not like a particle bouncing around in there. So this is really not a very accurate picture. This is not really a very good model of what's happening here. We want to treat it like a standing wave. A standing wave, remember, we can think of that as a wave traveling in this direction and a wave traveling in this direction that are adding constructively. And so we can think of these as 2 counter-propagating waves that add constructively, that are in phase with each other. And so we get a standing matter wave in the box. And so in this particular picture, I've shown the 3 lumper, but it doesn't have to be the 3 lumper. We could get the 1 lumper, the 2 lumper, or the 3 lumper. We could get any of these standing waves, and moving on, we could get more, right? One thing to notice here, as I go from the 1 lumper to the 2 lumper to the 3 lumper, the wavelength decreases. So as I travel in this direction, wavelength decreases. Whereas, as I travel in this direction, what happens to the frequency? The frequency increases. Now, the energy here, it's not as simple as h times f with the energy of a photon, but much like with a photon, an increasing frequency is an increasing energy. So not only does the frequency increase in that direction, the energy also increases in this direction. And so what we're doing is we're seeing that these different standing wave modes have different energy. Since we cannot get a wavelength, a standing wavelength, that is in between this and this, we cannot get an energy that is in between this and this. We cannot get a wavelength that is in between the 2-lumper and the 3-lumper. Therefore, we cannot get an energy that is in between the energy of the 2-lumper and the energy of the 3-lumper. So here we see that energy is quantized. It is not a continuous spectrum of energy that this particle can have. This particle can only take on discrete energies. And so we're actually going to name this by the energy levels. We're going to describe these as different energy levels. This would be the N equals 1 energy level. I called it the 1-lumper. That works too. It's a little more physicsy to call it the N equals 1 energy level. This is the N equals 2, and this is the N equals 3, and so on. We could keep going. The man who had the first idea for this was named Erwin Schrödinger, and he was an Austrian physicist, and he came up with the first real theory of quantum physics called quantum mechanics. In his theory, the electron, the proton, the neutron, whatever it is we're talking about, can be described by a wave equation. And the wave equation is that of a matter wave. And so the wave equation might take on one of these shapes. And each of these have a different energy associated with them. How are we going to interpret these wave equations? Well, we can think of them as standing matter waves, and that's a wonderful way of thinking of them. We can think of them as probabilities. We can think of them as probabilities of where the particle might be found, right? If you think about a wave, right? We could say, where is a wave? I don't know, I'm making a sound wave here. I created a sound wave in this tube. When I created a sound wave in this tube, could we say that the wave existed at a specific location? I don't really think we could, right? The wave certainly existed within this tube, but it made it out of the tube in the form of a traveling wave, and it made the speaker in my computer wiggle, and hopefully that's how you could hear it. But you know, it went upstairs, and somebody carefully listening could probably hear it outside. So where exactly was this wave? Where was the beginning of the wave, and where was the end of the wave? I don't know. It doesn't really have a definite answer, right? That question doesn't really have a definite answer. However, where is a particle? Oh, well, here's a piece of chalk. Definitely particle-like behavior. I can tell you exactly where this piece of chalk is. So, what if we wanted to know, where is this particle? Maybe it's an electron. Well, if we make a measurement and we say, I want to know where the particle is, well, we can do that, right? We can measure it and we can say, oh, the particle was right here, maybe. Well, that means it wasn't over there, right? So when I measure this thing, it actually, there's different ways that people talk about it. People talk about the wave equation collapses, is one way people talk about it. I don't know. I could measure the location of the electron. I could do that. I could set up an experiment to say, hey, you know, at t equals 14 seconds, where is my electron? Oh, I could measure where it is. So one way we could think about these matter waves is we could think about them as probabilities. And so we see that the electron is not at all likely to be here. In fact, it will never be found here. It is more likely to be found in the middle than anywhere else if we are in the n equals 1 energy state. If we're in the n equals 2 energy state, we can interpret this as the particle is much more likely to be found here and here rather than here. But the fact is, until we measure it, we don't know where the thing is. Okay, so this is Schrödinger's idea, and it's worked out fantastically. And so to take this a little bit farther, we can say, okay, much like we did for standing sound waves and standing waves on a string, we know that the wavelength of the nth mode is simply 2L over n. And we see that this works out great, right? So in this situation, notice that we're looking at 1/2 of a wavelength. Well, so that means that the wavelength is twice the length of my string, or of my box, I suppose, in this case. And so lambda here equals 2L. Notice here that we're fitting one complete wavelength here. And so here we have lambda equals L. What do we see here? Well, 2/3 of L equals lambda. So this is 2/3L equals lambda. And so notice that this jives exactly with this equation. And this is the same equation we got when we did standing waves on a string. It's the same equation we got if we were dealing with sound waves in a pipe that was open, open, or closed, closed. Where we're going to kind of take a different path here than we did with standing waves on a string and standing sound waves is each of these modes have different energies associated with them. And I'm not going to prove this to you, but it comes out of the Schrodinger equation that we could write for these waves. So these energy levels then are given by this equation here. And what do we see? Well, this is 1/2m, that's the mass of our particle, our electron, our proton, our neutron, whatever it is that we're dealing with. H, this is our good friend H, our Planck's constant, N is the energy level, and L is the size of our box. We can simplify that just a little bit to have it end up looking like this. And we have different energy levels. Now, that's pretty cool. So if we plugged in E1, we would get this. And notice then that this n squared here is next to this business here. And so we end up, we can simplify this to write the energy of the nth energy level is n squared times the energy of the first energy level. This particle cannot possess an amount of energy that is in between the E1 and the E2 state. It just cannot do it. N is known as the quantum number, and it describes the energy level of the particle in the box. So this is the basics of quantum mechanics, as developed by Erwin Schrödinger. Let's do a quick example. An electron is confined to a region of space of length 0.19 nanometers. This is comparable to the size of an atom. What are the first three allowed energies of the electron? All right, well, let's just use that equation and just see what we get. Okay, so we're going to find E1 first. We're going to use this equation right here. H, 6.6 times 10 to the negative 34th joules squared, mass of an electron, L is 0.19 times 10 to the negative 9th meters squared. And so we run our calculator, and we get 1.6 times 10 to the negative 18th joules. That is a tiny number, isn't it? Maybe this would be more useful if we ran this number in EVs. Let's convert. We're going to multiply this by 1 EV over 1.6 times 10 to the negative 19th joules, and we see that we get 10 EV. So E1 is 10 EV. Well, we can use this equation right here to calculate our next two energy levels. So this is E1. E2 equals n squared times E1. And so that is 2 squared times 10 EV, or 40 EV. Similarly, E3 is 3 squared times E1, or 90 electron volts. So those are our first three energy levels of this electron confined to a box. And to be clear, those are the only allowed energies that this particle can have. Now, it could have higher energies. It could have, n equals 4 would be 160 EVs, n equals 5 would be 250 EVs, and so on, right? So it could have higher energies, but you could never, ever, ever find this electron with an energy of, say, 15 electron volts. It just can't happen. This is what we mean by the energy is quantized. One other thing to point out is that, 0.19 nanometers, that's about the size of an atom, right? And so we should get energies that are sort of comparable to electrons in an atom. And we do. It turns out that it takes 13.6 electron volts to ionize hydrogen. So what does that mean? It means that the energy of an electron in the ground state of hydrogen is negative 13.6 electron volts, which means that if I add 13.6 electron volts to that, we can completely remove the electron from the atom, ionizing that hydrogen. And so that 13.6, you see that is comparable with the numbers we're getting here. And this is just a real basic model, right? We could think of a hydrogen atom as being an electron trapped in a spherical box. We're going to do that in the next chapter. So we could make an energy level diagram for this system. And so the lowest possible energy is called the ground state. Notice the ground state in this atom, in this system, I should say, is not 0. The ground state in this system is 10 electron volts. So our ground state is at 10 electron volts, and these are the excited states. Those are the only states that this electron could be in. It turns out that an electron can move between states by absorbing energy or releasing energy. And that energy gets absorbed or released in the form of a photon. And so notice here, it would take 80 electron volts to move this atom from the n equals 1 state to the n equals 3 state. Which means that if a photon came in that was an 80 electron volt photon, then this particle could absorb it and move into the n equals 3 state. Let's say that the particle was in the n equals 2 state. I don't know, it got there somehow. It could jump down to the n equals 1 state by releasing a photon. How much energy would that photon carry? Well, it would carry the exact energy that is the difference between these two states. So 40 minus 10 is 30. Therefore, if this particle, if this system, moved from the n equals 2 state to the n equals 1 state, it would release a 30 electron volt photon. This is what we call a quantum jump. And as far as we know, this happens instantaneously. So the particle might be in the n equals 3 state, and maybe it releases an 80 electron volt photon, and then it instantly jumps to the n equals 1 state. It doesn't travel through these other states. It just immediately goes from the n equals 3 to the n equals 1. So a quantum system in energy level I, so this is the initial, and it jumps up or down to some final, it gains or loses an amount of energy equal to the difference between those two. And so we always just say that this is a positive number. We'll use absolute values here. The jump will correspond to the absorption or emission of a photon with frequency equal to this. And again, this is just using our equation for the energy of a photon. The energy of a photon is h times f, and the system will absorb a photon if it's moving up in energy level, and if it's moving down in energy level, it will release a photon. Why don't you try one? What is the maximum photon energy that could be emitted by the quantum system with the energy level diagram shown below? Why don't you try it out and pause the video? I'll see you on the other side. Well, maximum photon energy. To get the maximum photon energy, we're going to have to move from the highest energy level to the very lowest energy level. Again, notice that in this system, the ground state is not 0. In this system, the ground state is 1 electron volt. So the maximum energy that could be released would be 6 electron volts. Not too bad. How about this one? What is the minimum photon energy that could be emitted by the quantum system with the energy level diagram shown below? So what's the smallest energy? Why don't you think about it, and I'll see you on the other side. Well, the smallest energy that could be emitted, the lowest photon energy that could be emitted, well, let's see. 7 to 4, that's 3. We could have a 4 to 3 transition, couldn't we? That's 1 electron volt. There's not going to be any choices smaller than that. Indeed, it is 1 electron An electron in a quantum system has allowed energies E1, E2, and E3. Draw an energy level diagram and determine what wavelengths are observed in the emission spectrum of this system. Okay, so the energy level diagram, that's not too bad. We've got E1 equals 1 electron volt. E2 is 4, and E3 is 6. And I'm going to try and kind of draw them somewhat proportional. Notice this does not fit our pattern of, E sub n is n squared times E1. E2 fits all right, but notice E3 would be 9 if that was the pattern. So this must not be just a particle in a box. This must be a more complicated system. I don't know what it is, but here's our energy level diagram. That's great. So what wavelengths are observed in the emission spectrum of the system? Okay, so we've got two excited states, one ground state. You always only have one ground state. Two excited states. So I actually see that we could get three different photons out. We could get a transition from E3 to E2, from E2 to E1, or E3 to E1. Let's figure out what wavelengths are associated with those. So E3 to E2, that is 2 electron volts. So we can get a 2 electron volt out. We've got E3 to E1. That's 6 minus 1, 5 electron volts. And we could get E2 to E1. And this would probably be better like that. And E2 to E1 gives us what? 3 electron volts. Okay, so those are our photon energies. We know that E equals H times F. As we've done a number of times, we can write this as Hc over lambda, which means that lambda equals Hc over E. So this is a good time to use H in EVs. So we're going to do 4.14 times 10 to the negative 15th. Divided by the energy, and so let's go ahead and do E3 to 2. For 3 to 2, we have 2 EVs down here. And we run our calculator, and we got, going ahead and converting to nanometers, 621 nanometers out of that. Okay, that's in the visible spectrum. It's a reasonable answer. It turns out, the math is exactly the same, just our denominator changes. So for lambda 3.1, we get 248 nanometers. And for lambda 2.1, we get 414 nanometers. So that is our emission spectrum from this system. Notice that the larger the energy, the shorter the wavelength, as expected. Also, the higher the frequency. Okay, so that means that these are the only wavelengths that can be emitted by this system. No other wavelengths can be emitted. And if we have the system in the ground state, and we'll learn that systems tend to exist in their ground state, then these are the only wavelengths that could be absorbed as well. Okay, why don't you try one? An atom has energy levels shown. How many spectral lines are in the emission spectrum? Why don't you see if you can't figure this out? I'll see you on the other side. Well, let's just start counting. I really don't know how to approach it other than that. Here we have 0 EV, 3, 5 EV, and 6 EV. And let's go ahead and we'll just draw some transitions along with the energy associated with them. So we've got that transition. That is 1 electron volt. We can do that. And of course, that is 3 electron volts. Then we can do this. And that is 6 electron volts. That difference. From the second energy level, we could go here to here. And so that is 5 minus 3. That's 2 electron volts. We could go also 3 to 1. And that is 5 electron volts. Now, we could also go 2 to 1, couldn't we? Let's draw that in here. We could go 2 to 1. How many electron volts is that? That's 3 electron volts. Ooh, but look at that. We already have 3 electron volts showing up there. So, while this transition can certainly happen, it is not a separate spectral line because it will not create a different color. It will not create a different wavelength and frequency. It's the same wavelength and frequency as this spectral line. So we're just not going to count that one. It certainly can happen. But it won't create its own spectral line. So how many do we have? 1, 2, 3, 4, 5. 5 emission lines in this spectrum.